Hello, I'm Thandat Trong. In this presentation, I would like to share our recent work entitled FALCON, Fairness Learning via Contrastive Attention Approach to Continual Semantic Scene Understanding. This research study is a collaboration between the University of Arkansas, Google DeepMind, Carnegie Mellon University, and MBZoo AI. This research has been sponsored by the NSF DART project. The goal of continual semantic segmentation is to learn the segmentation model in dynamic environments. Specifically, it seeks to learn novel classes of data while preserving the knowledge of classes learned previously. Under these learning scenarios, 3 challenges have been identified. Firstly, the catastrophic forgetting problem signifies the model's inability to maintain previous knowledge when learning on new training data. Secondly, the background shift problem depicts the problems of the classes of previous or future data that have collapsed into a background class. Thirdly, the fairness issue refers to the model's biased behavior between major and minor classes due to the imbalanced data distribution. In the context of continual learning, the data distribution of classes often exhibits an imbalance. Specifically, major classes tend to occupy a large portion of the image or occur more frequently compared to minor classes. Consequently, this imbalance leads to a bias in the model's predictions, favoring major classes. Although the first 2 problems have been extensively studied in prior research, the fairness problem, a significant challenge, has yet to be adequately addressed. To address the fairness problem, we introduce a novel fairness learning via contrastive attention approach, denoted as FALCON, to continual semantic segmentation. In particular, first, we introduce a novel contrastive clustering paradigm to continual learning that models the catastrophic forgetting problem. Second, by analyzing the limitation of vanilla contrastive clustering in biased data, we introduce a novel fairness contrastive clustering loss to model the fairness problem in continual learning efficiently. Third, to effectively model the background shift problem, we introduce a new attention-based visual grammar that models the topological structures of feature distribution to handle the unknown classes effectively. Finally, our ablation studies illustrate the effectiveness of the proposed approach in different aspects of fairness promotion. Compared with prior methods, our approach achieves state-of-the-art performance under different settings on 3 standard benchmarks of continual semantic segmentation, including 80-20K, Pascal VOC, and Cityscapes. In our approach, the segmentation model will extract the feature representations. Then, we model the continuous learning objective as a contrastive clustering loss, where features belonging to the same class are pulled closer, while features belonging to different classes are pushed away. However, the vanilla contrastive clustering loss will behave unfairly between major classes and tailed classes due to the imbalanced data, leading to the clustering of tail classes being scattered. Therefore, to address this problem, we propose a new fairness contrastive clustering loss by introducing a learnable transition vector v and a scaling factor alpha. In our design, the scaling factor alpha will help to rescale the impact of the enforcement between features and clusters. Meanwhile, the transitive vector v assists in translating the center cluster into the proper position of the latent space. Our approach promotes the compactness of clusters in the minority group. In our contrastive clustering approach, the centroid vector of each cluster play a role as maintaining the knowledge of classes to avoid the catastrophic forgetting problem. Then, to address the background shift problem, we propose a new attention-based visual grammar approach to model the unknown classes. In particular, while feature representations differ across classes, the distribution of features around each cluster tends to be similar across clusters. As a result, by learning these distribution patterns, we can identify whether a feature belongs to a specific cluster. Then, given an image at learning step T, the learning process of our proposed FALCON can be summarized as follows. The model will compute the semantic segmentation loss with the predicted segmentation. Then we apply the fairness contrastive loss into the feature representations extracted by the segmentation model. For the unknown features, we use our attention-based visual grammar model at learning step T-1 to assign their clusters. To learn the visual grammar model at learning step T, we use the known clusters and features at the current learning steps to update the model. Let's take a look on our video demo. As shown in the video, compared to prior method, our model can identify the unknown classes. In particular, our method can classify different unknown classes based on the assigned clusters via the attention-based visual grammar model. Compared to the prior method, our approach produces better segmentation with a clearer boundary and accurately identifies classes. Thank you for watching.